the homework from yesterday and the quiz from yesterday. So let me just show you though. Some of you are saying, wait a minute, I did the homework, I did not receive it back. Now, eventually, and I actually have this in my office, I just haven't implemented it yet, and this also gives me a chance to learn names by handing back the papers. But I have a file folder that I will bring here that I'll stuff everything in, and then you won't have to take all your papers every day. You could take them once a week. You could ignore the file folder, and I will just accumulate your papers till the end of the semester, and then I will shred them all. But whatever this, you can make that choice. But in that file folder, there will be a folder. Let me just show you here just a sec. Where's my camera? Camera. Yeah. In the file folder, there will be a folder that is titled Unnamed Mathematicians. And so these are two prime examples of unnamed mathematicians. Excellent work. They got check marks. No credit though. So if one of these is yours, you can come see me afterwards, put your name on it, and I'll give you credit. Also, if for some reason you chose not to do the homework for yesterday, you can always hand it in today, and I will give you credit for it then. So late work is better than no work in my book. So usually if it's just a day late, even though my syllabus says that I take off 2% a day, it's too much of a hassle for me to figure it out. So I wait till it's about, I don't know, if it's a week or so, then I start taking off points, and I'm like, yeah, 10 points off. So anyway, that's that. So the second thing is, if you haven't had me before, class will begin with prayer, and then we will have time to talk about the homework that you did. And I've already got people begging for mercy and help on numbers 40. What was it, Michael? 45 and 47? Okay, yeah. So let's take a look at these. So we'll always have time. If you have issues with the homework, I'm happy to do this. I've budgeted time to do this. So let's take a look at number 45 is first. And one other thing I should say is I should have brought it with me. I think I might have some. So there are a couple of people who said that their textbook was like an early Transcendentals or a late Transcendentals, the wrong version. And if it doesn't line up perfectly, I might have something to help you out. I'll try to remember on tomorrow to check it and bring it. If I've got like a different edition, but anyway. So we'll see if we can work things out for those of you who are still struggling with which text and so forth. But number 45, make sure I have this right, because if we have different problems, I want to do the one that you want me to. So this is this one, 1 plus x over 1 plus x squared. Does that look right to you, Michael? Excellent. So this one is there's a little trick. Once I do the little trick, you're going to say, oh, of course. In this case, your temptation, and actually the correct thing to do, is to do u substitution, where u is equal to 1 plus x squared. And then du would, of course, be 2x dx. And here is the problem that you bump into. And that is, how do you isolate the 2x dx given that integrand? Because what you would want to do is you would want to factor x out of the entire integrand so that it could be smashed up next to the dx. The 2, of course, we don't have any problem with. You can manufacture a 2 easily, but the x is the problem. So here's the trick. And once I do this, you'll be, oh yeah, of course, it's simple, but I'll finish this anyway. And that is that you take this fraction and you change it like this and turn it into 2 fractions using basic algebra. And then you treat these separately. So now that I've got that, we can do this, 1 plus x squared dx, and then this other one, x over 1 plus x squared dx. So this substitution that we all thought of is the correct substitution for that integral. So let's do these separately. This won't take long now. So I will come back to do the first integral in just a minute. The second integral, though, we're going to write down like this. Integral of 1 over 1 plus x squared times 2x dx. And of course, you know what the 2, we can just put a 1/2 somewhere. You probably are more comfortable putting it out front, but I ran out of room, so I'm putting it there. And now you can see exactly what's going to happen using that substitution. that thing will become just 1 over u times 1/2 du. So this is my du. The 1/2 is just going along for the ride, and the 1 over u is there. So now it's like, yeah, okay, so let's just finish this up. We all know that this is going to be the natural log of the absolute value of u, plus c, I guess. Antiderivative of 1 over u, natural log of the absolute value of u. Hopefully you remember that. And then, of course, we will go back to x, and this will become 1/2 natural log of 1 plus x squared. Okay, well, let's deal with this thing on the left now that we've got the right. The right is where the substitution is. So are there any questions about this right-hand side? Any of that? So Michael, you're good with that? Yeah? The one, huh? What do you mean? Yeah. So I took this x, shoved it over here because because I wanted it to look exactly like the substitution. So that's that one. Any other issues with any clarifications? Okay, let's deal with the one on the left now. That one's my favorite, and I should have brought my my mug. Some students knew this, and back in 2020 they gave me a mug that they had laser etched with this antiderivative on it. So if you want to know what to get me at the end of the semester, a mug with, I don't know, some other theorem or something. Fundamental theorem of calculus would be fun. But anyway, you don't have to get me anything actually. Just get an A in this class and I'll be thrilled. But getting back to this here is just antiderivative that we should all know. It's arctan of x. That's it. So the antiderivative, make sure you know that one because it is my favorite. It'll be on various tests and quizzes. It's not on this quiz today, but it might pop up. Here, I'll write it down. So the final answer here is just arctan of x. I don't know why I like it so much, but it's just sort of fun that the derivative, so I'll write it like this, the derivative of arctan of x. I think this is, well, I don't know what's on my mug. I'd have to look at it. But that's the derivative of arctan. I guess what I like about it is that you have a transcendental function. Arctangent is transcendental, meaning that it can't be written in terms of just basic polynomials. And the derivative of that transcendental function is just this easy rational function. So it's kind of cool. And so the antiderivative, of course, of this is equal to arctan of x plus c. So here's the final answer, by the way. Yeah, but the important thing to note from this is that if you have a fraction, you can do algebra with your fraction and separate that fraction into two fractions. That's totally legal. Algebra is good. And if you're doing poorly in calculus, usually it's not because you don't know calculus. Usually it's because you don't know algebra. So I know that that's terrible, but it's the truth I've found in the past. Okay, other issues with 45, and then we'll go on to 47. 47, you said, was the other one? Okay. So yeah, like I said, I'm happy to help, and I love especially if you have something specific. But once I looked at 45, I knew what the specific question was. Let's take a look at 47. So that one is very similar to one that we did near the end of class last time. I'll get us started, but I won't finish this one. So this one, the big problem is that x there. I don't have any problem with any of the rest of this. It's that first x. So that when I do my substitution, and if you chose this for your substitution, you're doing great. What happens is that you can, you're going to rearrange this. So here's x, 2x plus 5 to the 8th. And then you're going to put a 2 times dx here, and that has to balance with this 1/2. So the original problem I've rearranged, and here's the issue, is that I can deal with this. That's going to turn into du. I can deal with this. This thing is going to turn into u. But then what happens with this thing? That x there, that's the big problem. What do I do with the x? And so you might have missed this at the very end of last time. We had a problem sort of similar to this. And what you do is you just rearrange that u, solve for x, and you get x is equal to u minus 5 over 2. You can do the algebra. I have faith in you. Well, maybe I have hope. But anyway, now we have this x, and so the replacement looks like this: 1/2, integral of u minus 5 over 2 times u to the 8th times du. So there it is after all the replacements. There is still a little bit of algebra you need to do. Don't forget to multiply through before you do your antiderivative. So you'll have 1/4 times u to the 9th minus 5u to the 8th. So the 1/4, I'll write it, but then the rest of it is pretty straightforward. So it'll be 1/4, this is the integrand, times u to the 9th minus 5u to the 8th. And then you're going to do your antiderivative of that, which is simple because it's a nice polynomial. So the rest of this should be pretty rote for you. All right, what other issues did you have? Yeah, what do you think, Ryan? 37? What was wrong with 37? Oh, it's my favorite function yet again. Well, now that we've seen this, you should be able to do 37 pretty easily. Let's just take a look though, just to make sure that you see the connection. So 37 is the arctan squared over 1 plus x squared. Does that look right? Am I getting the right one here? Oh, 31. Is that the one you wanted? Sorry.
No.
Which one? 37? Oh, it was just hopeful. I guess I just zeroed in on that one because it's my, yes, okay. Never mind. This is not 37, it's 31. It's this poor eyesight that just keeps getting worse as you get older. It's amazing. I remember when I was your age and I would have like some piece of paper that had like my license had like 1-point font on it that I could read perfectly. And my dad, he'd be like, oh, I gotta get my glasses. And I used to make fun of him. And now I'm my dad. It happens. If you live long enough, you have to deal with these things. But the alternative is kind of tragic. So I'm thankful. So 37, let's deal with 37. What is this? Hyperbolic sine. Okay, so what are you, not familiar with hyperbolic sine? Apparently not. Okay, so let's do this. Is that squared or cubed? Where is it? It's squared times hyperbolic cosine. Oh, now you got it? Okay. Well, anyway, I'm going to use the u is equal to the hyperbolic sine. Du, the derivative of hyperbolic sine is hyperbolic cosine. Derivative of hyperbolic cosine is hyperbolic sine. So, you know. Anyway, so this will be like this. And so then the rest of this is pretty straightforward so that you end up with the integral of u squared du. I don't have to do any rearranging there. And that's equal to u cubed over 3 plus c, which is equal to the hyperbolic sine. Cubed over 3 plus c. By the way, hyperbolic cosine, if you have ever seen, so hyperbolic sine, let's see, sine h is e to the x minus e to the negative x over 2. Hyperbolic cosine is the average of e to the x and e to the negative x. And these are important, especially in certain applications. One interesting application, if you're not familiar with it, is if you take the hyperbolic cosine and turn it upside down so you negate it, it looks like this, which looks like a parabola. It's not a parabola. This is what's called a catenary. And this is, oh, I guess I could do it upright as well. There's the hyperbolic cosine. Anyway, if you turn it upside down, what you get is you get the St. Louis arch. And if you have it upright like this, this is if you hold a rope suspended from 2 points, you get a catenary, which is the hyperbolic cosine. So it's just interesting function. But we should probably look at other issues with substitution. So that was just maybe not being as familiar with the hyperbolic functions as you might want to. Are there any other things with the mechanics of doing the substitutions? Because that's all I got. I got a couple of practice problems for your quiz. Nice, easy. I hope we all get hundreds on it. Let's see, what do we have here? Those I'm going to set aside. All right, well, if no one has any further questions, let's go ahead and I'll put the quiz out here. Let's see, I've got it on here. Here's the actual quiz for the people watching from home. And I'll just pass these around in back row. Remember, I promised that this time I would go to you first. So you get a little bonus couple of extra minutes while I goof around trying to get everything. What? He never showed? I think he mentioned he wouldn't be here. I'll just take that stuff. I'll come get it in a minute. You just want two? See if that's two. There, you want one and I need, here's two. Sorry about that. What's that? Oh, yeah, sure. Decor. There's one more. Here, I don't know how many are there. You can have extras. You just need two, don't you? One over here. Here, is this for me?
Yeah.
Oh, thank you. It's like a little gift. Does everyone have a copy of the quiz? Wow, I've got extras. I guess I better do my attendance. Nice. It's not here. And hopefully you're coming down the home stretch. I'm going to do my attendance while you're finishing up. If you are done, feel free to turn your paper over and send it towards the middle here, and I'll come get it in a few minutes. Any extras can go towards the middle as well. Apparently I had too many today. All right, submitted. So, all right, so try to wrap things up, and then we'll go over the quiz here. Nice, excellent, good job. All right, back row, you did it. Good job. Just finishing things up. All set. All right, good job, Hunter. Michael, thank you. Getting that last thing there, very nice. All right, good job. Thank you. All right, almost there. I'll come back around to get it. All right, thanks. All right, so now you're going to try to finish up that last problem. Put that last number down. So we don't need this. I'll come back up. Polish it off here. Looking good. All right, thanks, Landon. The back row's all set. Good job. Excellent, thank you. What's that? Oh, sure. You didn't want to give it to me earlier? Yeah, that one. I don't want that one. Yeah, that one. Yeah, you can keep that. I'll take this one. Yeah, you too? You're holding out on me? Okay. All right. So if you're still stewing over them, just put down the substitution that you would use. That's at least a start. And then I'll be able to give you a generous grade. I don't know if you've noticed, but on the quizzes, I'm usually pretty generous. It's more of a practice. Uh, Final answer. Very nice. Good job. All right. Any others? Are there any other holdouts? Okay, great. Let me see. I have them all in my hand. Yes. Staple them together. Oh, come on. This is why I like to bring my own stapler, because this one doesn't always work. Okay, we're good. Okay, so let me show you what I did. Hopefully I got them right. I didn't look at, usually I'll look at the answers that you give me and I'm like, oh, I made a mistake. So sometimes I'll come up here and just quietly fix. But I didn't do that. I don't know if hopefully I got them right. But anyway, so this first one, hopefully you did the obvious thing, and that is to make the substitution for this thing here. So that's the pretty obvious substitution. And then a little bit of calculus later, you end up with 2/3 x squared plus 3 quantity to the 3/2 power plus c. So not too bad. The main thing, I guess, to remember is the integral of the square root of u is 2/3 u to the 3/2 using the power rule, because square root is u to the 1/2. Then the second one, it looked suspiciously similar. However, the thing under the radical was what was different. And so that had to do that trick that we talked about and take your substitution. So if you wrote this down, you're doing great. And then here's the trick, is making that little algebraic manipulation so that this becomes x equals u minus 3. But then the rest of this, very similar. I guess that if you don't remember how to deal with radicals, integrals, this is a good practice for you. I should have had fewer of them here, but here we are. Anyway, so the final answer here is this mess down here. Like I said, this one I did mostly in my head here, so things might have gone awry. Hopefully I got it right, but I'll check when I do your answers with your quizzes. And then the final one, hopefully you saw this one was also another one that was hopefully pretty obvious to you, that this would be the substitution. U is equal to that thing down there, because the derivative of that thing down there is x cubed. So we have x cubed dx. So here's x cubed dx. The only thing we needed to manufacture was a 4. And so when I threw that 4 in, that's what I got. And then the rest of this, antiderivative of 1 over u is natural log of absolute value of u. And then I had to plug in my limits, ended up with this. If you were really clever, I suppose you could have written this like this, natural log of 2 to the 4th root of 2. It's the same thing, using the rules of logarithms. But yeah, hopefully you know that the natural log of 1 is 0. This also, let's see, natural log of 2 is what, 0.69. So this would be about 0.175 or so. So if you did it on your calculator, you could I would mark that right. Okay, let's move on. Okay, so what are we doing? We're doing areas between curves today. This hopefully will be a happy moment for you, because at the end of last semester, or at the end of Calculus 1, you learned about computing areas under curves. All we're going to do today is we're going to say, instead of doing the area under a curve, we're going to do the area between curves. Now, you remember I promised that each time I do this, I'm going to put a little rectangle to represent the idea that we're going to take our Riemann sum, or at least have that in the back of our minds to help guide us as we set up the integral. It's going to be important for what we do. So to warm us up, though, I've got a very simple problem to start us off with, and that is I'd like to know the area under this curve, 9 minus x squared, between x equals 0 and x equals 1. So that's our first nice, easy, just to remind you about what you did back at the end of Calc 1, finding areas under curves using a definite integral. Hint, hint. So go ahead and see if you can do this. Work with a friend. And meanwhile, I will just switch over so that I can write on this in Notability. Okay. Okay, let me show you what I've drawn so that you can, you might have had something similar to this. I've got this graph, 9 minus x squared. Hopefully you're familiar with this nice, easy parabola pointing downward because of the negative. Starts up there at, the peak is at y equals 9. But I'm going to do something that might be a little bit different than what you did near the end of Calculus 1. And that is that I'm going to put a little rectangle in here just to guide me. If we were to do this using a Riemann sum, this would be one of the many rectangles that you would have to draw and compute the area of. However, the reason why I do this is to guide me in terms of what this integral is going to look like. The small side of that rectangle, I'm going to label as delta x. The tall side of the rectangle, so the tall side is f of x. In this case, f of x is 9 minus x. So far, so good. Orienting you to my little diagram. And so, and now at this point, we won't always do this, but if I were to write this as a Riemann sum, I would write it something like this. I would write a sum. I'm adding up a bunch of things. And what I'm adding up is I'm adding up a bunch of rectangles, and those rectangles will be the height of the rectangle times the width of the rectangle. So this up here, all that means is I'm adding up a bunch of stuff, and the things that I'm adding up are the height of the rectangle times the width. And of course, there are going to be a bunch of these. I'm just writing one of them, but there would be many of them down here. And I'm just drawing one representative. And the reason for this is that it will guide me as I think about what this is going to look like when I write it as an integral. So notice that the integral looks almost exactly the same, except for the delta x turns into dx, and the summation symbol turns into an integral symbol. So as we get harder problems, I'm going to use this same strategy. Draw a little rectangle. I'll sometimes write it as a summation just to say this is what we're doing. I don't need, I mean, we could try to put limits here, but I'm just using that as a stepping stone to help me to know what the eventual integral will look like. Anyway, now you probably just did this when you solved this, is you said, okay, this is going to be the integral from 0 to 1 of 9 minus x squared dx. That's totally fine. You don't have to draw the rectangle yet. You will soon. But for now, you don't have to draw the rectangle. You don't have to write the summation. So those are just helpful things to guide us to get to this point. So if you got to this point without writing all that, great. However, in the future for this class, I'm going to want you to put a little rectangle on your graph. So the next one, put a little rectangle there. Anyway, the rest of this is easy. This is just going to be, so easy that I'm just going to pick someone. You can do it for me. So Eli knows the antiderivative of 9 minus x squared, don't you? Very nice. Okay, so we've got that, and we're going to evaluate this from x equals 0 to x equals 1. And so here I'll just do this because you can all do this. It's 9 minus 0. And so this ends up being 26 thirds. Is that right? Okay, so that's the area there. Very nice. Good job. Okay, next, second problem. So first problem, super easy. Second problem is also similarly easy. Same idea, only I'm going to find the area of a different curve. So here's the different curve. So x squared minus 2x plus 9, same limits. So I'll give you a minute to do that, and I will goof around up here with Notability while you're doing it. what we got? X squared. Sorry, it took me a minute to redraw everything. Okay, I've got it. Okay, I've got this thing redrawn. Let me show you what I have here. How's that look? Okay, so I basically took the original picture I had up there, which wasn't very good to begin with. I brought it down here. I should shrink that rectangle, shouldn't I? But you get the picture. So we're going to do this thing once again, set up our integral from 0 to 1. And of course, the integrand now is x squared minus 2x plus 9. So I guess we need to get this antiderivative. Similarly easy to the first one. You aren't here to do it. And Caleb is here, though. Caleb, where are you, Caleb? Caleb, there you are, Caleb. Okay, what's the antiderivative of x squared minus 2x plus 9? Very nice. Okay, so we're going to plug in the limits, x equals 1 and x equals 0. So x equals 1, I get 1/3 minus 1 plus 9. 0, I just left it there because I knew it was going to be 0, but you should always check because sometimes it's not 0, so don't just assume. Okay, so let's see, I guess I could erase this stuff down here. And then 1/3 minus 1, that's negative 2/3 plus 9 is 25/3. So 25, got a little excited there. So that's 25/3. Okay, good enough. So hopefully you got this so far. Okay, last thing is to combine these two because what we're dealing with is areas between curves. And so what I really wanted to do was to do this. I want to find the area between these two curves. And to do that, here's the new picture. You can kind of imagine what we could do is we could take the old answers that we had and just subtract them from one another, right? The upper curve has an area underneath it of 26/3. The lower curve, this one, has an area of 25/3. And so, and by the way, I cleverly chose my limits to be where these two intersect. They intersect at x equals 0 and x equals 1. And so the area between those curves will be that the difference between those two. So now that I've done all the work, I might as well just go ahead and do this. 26/3 for the upper curve minus 25/3 for the lower curve, which is 1/3. So that little tiny sliver is 1/3 of a unit in area. All right, well, how are we going to do this in general? Here is the rule. So I did this in little stages here, but in general, it's much quicker if we just do it all at once instead of doing step by step. And so here's the rule, and that is that you're going to first sketch your area. And I'll do this in just a minute with a nice simple area. You're going to add a typical approximating rectangle to your sketch. So always put that little rectangle there. There's a reason. And I'll explain it in just a minute. There's a good reason for doing that. It seems superfluous at this point, but there's a good reason. Then you're going to integrate. This isn't rendering properly, so I will just write it here. This minus this. There we go. I think that's what that's supposed to be. Let me double check on my computer. The iPad sometimes doesn't render my equations properly. There we go. Okay. Yeah, that's good enough there. Okay, let's do this. Let's do an example, and then I'll show you why. We'll come back to this slide because there's one more step that I haven't shown you, but it'll show up here in just a minute. But it's not pertinent yet, but it'll explain why I want you to sketch and add an approximating rectangle. So let's do this one here. This one's nice and easy. I want to find the area between, so I suppose I should put a stem, like an explanation here. Find, that's terrible, the area between, dot, 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 those two curves. Find the area between those two curves. Now you could probably graph these pretty easily, but I think we all know what they look like. Those are both parabolae. One of the parabolas points upward, one points downward, opens up downward. So the one that is positive x squared, it's a parabola that opens upward. And the parabola, the first one, the one with the negative x squared, it opens downward. So those are the two parabolae that we're going to use. Let me just graph them for you. That'll save you some time. Here's what they look like there. So the first one is this one that's opening downward, goes up to the 12, and then it works its way down. And then this bottom one opens upward, or the second one opens upward. So take a minute. So we've got our sketch. The next step is to add an approximating rectangle. So a representative of the Riemann sum. What does that rectangle look like? So take a minute, sketch this on your paper, and then add a little rectangle, and we'll see if your rectangle looks like mine. All right, does everyone have a rectangle of some sort? Okay, let me show you what my rectangle looks like, and then we'll talk about why I put it where I did. So I'm going to put my rectangle. Here's something that doesn't matter. It doesn't matter where, left and right. Like, I don't care if it's over here. I don't care if it's over here. It doesn't matter to me. Just pick somewhere that's reasonably blank and put a rectangle. In reality, a Riemann sum would be a whole bunch of rectangles. I'm just picking one to represent them all. And so this one, I'm going to put it over to the left. You could put yours to the right. I don't care. The important thing, though, is wherever you put your rectangle, that rectangle should be a skinny, tall rectangle. And the top of the rectangle should touch the upper function. So it would be something like this. And the bottom of the rectangle should touch the bottom function. Now, if you made your rectangle touch the x-axis, that's understandable because that's what we've been doing up until now. But now we're going to do it using both curves. So notice that if you can imagine, if I were to compute the area between these two curves, I would break this up into a bunch of rectangles, compute the area of each of these rectangles, and add up that area. Okay, so let's deal with this rectangle really quick. This rectangle has a little side. The small side is delta x. So delta x is that little side, the thin side. What about the height? The height of that rectangle. Okay, well, the height of that rectangle, I'm going to name these functions. The first function I'm going to call f of x. And the second function I'm going to call g of x. So on this graph, the top one is f of x, and the bottom one is g of x. And I want to know, what is the height from here to here? How tall is that rectangle? And rather than randomizing, I don't want to put anyone on the spot, but does anyone want to volunteer? You know what that height is? You got it, Americo? Yeah, it's the top minus the bottom, right? So whatever this is, wherever you are, left or right, you would take whatever function value up here, subtract off this function value, and you'd get the height of that rectangle. So very nice. That's going to be f of x minus g of x. Perfect. So now you can see why I'm going to do this. Now I will write it like this. This is a little bit somewhat unnecessary, but I really like writing the sum, at least the form of the sum. So we're adding up a bunch of areas. Those areas, the area of that rectangle will be the height times the width. So you have the height that Americo gave us times the width, which is that little delta x. So the height, f of x minus g of x, times the width. However, despite the fact that I just wrote that, you probably won't write that every time you do a problem like this. Ooh, and we have 10 minutes to do as many problems as we can, apparently. It's okay. And there's only one more that I absolutely have to do, and then the rest of them you can hopefully figure out. So now we write this like this. So you turn that into an integral from, we need to know the limits. Okay, so technically, I won't make us suffer through this. Technically, we would actually have to figure out where these limits are. So I would do this. 12 minus x squared is equal to x squared minus 6. Solve, and I'd get x equals plus or minus 3. So technically, I should do that, but given the time, I don't want to do the algebra. So let's just say that we did do that algebra to figure out where those limits are. And then f of x is the top curve, 12 minus x squared. The bottom curve is g of x, so subtract off x squared minus 6 dx. And that's going to be, once we do this integral, I'll do this quickly given the time. I want to get through this. So this is 18x minus 2/3 x cubed, evaluated from -3 to 3. And I can't push this over any further, so I'll just, we'll do the answer really quick. So 18 times 3 is 54, minus 2/3 times 3 cubed, which is 18. So 54 minus 18 is 36. And then when I plug in the lower limit, I get -54 minus -18, which gives me a total of -36. So I have positive 36 minus -36, which is a total of 72. So I believe that's the right answer, if my mental of math is correct. If I got it wrong, then you'll have to forgive me. So I want to do at least one more. There's one more problem that we got to do. And then the rest of it, we'll deal with tomorrow, but it's not difficult. This is not hard stuff. Hopefully it's like, oh, this is just like what we did at the end of Calc 1. And it really is. Okay, so here's my next example, just to show you what what something that might be a little different would look like. So let's find the area between these two curves. X is equal to 2y squared and x plus y equals 1. Let me graph these for you. But I think probably even before I graph them, you probably notice the issue that you're going to bump into. And that is that I have x is a function of y rather than y is a function of x, which is annoying, but I can do it. I can graph these. That just means that that parabola opens to the right. X is equal to 2y squared looks like this. X plus y equals 1 is easy. That's a nice straight line. So I'm interested in that area between those two curves. Now here's the deal with this particular area. If I draw a rectangle, a representative rectangle that looks like this, what that means is that I'm committing myself to chopping this particular area up into vertical rectangles. And notice what happens with those vertical rectangles. Over here, those vertical rectangles touch the parabola on top and the parabola at the bottom. Over here, those rectangles will touch the line and the parabola. And so this is going to make things extra hard for me. So I'd prefer not to do this. So instead, I'm going to actually make this with a horizontal rectangle, which is kind of counterintuitive, especially when we just went through Calc 1 and everything was like a function, y was a function of x. But here we can shift our focus, we can do this. Now the side of that that's delta y, is the little side. And then the big side, so this, I'm going to have to figure out, but I can figure that out. That's not too bad. This function here is x is equal to y squared. The line I could write like this, 1 minus y, just solve for x. And so if you think of it about it, the difference between the right-hand side of this rectangle and the left-hand side is the x value of this line minus the x value of this parabola. And so I can do that. The x value of the line is 1 minus y. So here I guess I need to have more room. So I have 1 minus y. That's like the top function, or if you turn your head on its side, you could do this. And then minus the bottom function is y squared. So let's just pause for a minute, because this can be challenging. This is difficult when you have to shift your focus from up down to left right. It's hard. So I want to give you a chance to digest, and if you have questions like why is it this, or where did that one come from, I'm happy to try to answer them. Yeah, so this is going to be the most challenging thing on your homework is dealing with these, Hayden. We sure will. Mm-hmm. Absolutely. So when we set up this integral will have y as its the limits will be in terms of y. So certainly we're going to have to do that. So let's actually do that. That will explain maybe some of this. So my summation is going to look like this. I have 1 minus y squared. Oh, sorry, 2y squared, my bad. 2y squared, I forgot it's 2y squared. Sorry about that. So I have that is the width of the rectangle times the height, well, the delta y. So that's what my summation is going to look like. And then that turns into this integral. And we'll get those limits, Hayden, don't worry. So I have 1 minus y minus 2y squared, and this becomes dy. So there's where, so this is why I'm so interested in drawing these rectangles, writing down the little delta y and delta x. Anyway, let's get the limits because I need to know. Hayden did a good job of taking a guess, but we're going to find out for sure. I need to know where these two curves intersect, and I can find that out by setting them equal to each other. So I have 2y squared plus y minus 1 equals 0. Certainly you can factor this, can't you? 2y and y equal to 0. One of these will be positive, one will be negative. I think it's going to be a plus 1 and a minus 1. Okay, good. So that means that we have y equals negative 1. That's from the second factor. Sorry. So the second factor gave us y equals negative 1. That's this point. And this one is y equals positive 1/2. That's from the first factor, setting that equal to 0. So at any rate, this is going to be this limit, or these are the limits. Y equals negative 1 and y equals positive 1/2. And then from this, we have a nice polynomial. You can easily do this. You're just going to do your antiderivative the way it is. Now, I want to, in the last couple of minutes, assure you that if this is so uncomfortable that you cannot stand it, there is another option. So I want to show you that other option. But before I do that, I'm about to erase what I have here. So to show you the other option. So I want to see if there are any other questions. And like I said, I haven't finished this one. I have to take this, take that, and I'm gonna do the antiderivative. But you can, well, that was, whoops. Oh, now that's in there. Okay, let's just get, I guess it's gone. There. Yeah, there's my other option. Let's go back. Okay. Well, if you can remember what I just erased, you can ask questions about it. If not, here's the other option. So the other option is this. You might say, I cannot stand this. This is too much for me. I cannot take dealing with y as the special variable. Well, you're going to have to get over yourself at some point. But here's the secret, is I can take both of these and, oh, look at that. That's weird. And I can rewrite them. So here's what I'm going to do, is I'm going to rewrite them like this. Let me rewrite them first, and then I'll explain why. And then this is y plus x is equal to 1. Okay, here's what I've done when I rewrote, is I took all of the x's over here, and I turned them into y's. And I took all of the y's over here and turned them into x's. So you see what I did there? If I can solve this, the answer will be the same as this. I've just changed the labels, that's it. And you could change these to the initials of your first and last name if you prefer, whatever you want. But I'm just changing it to change the y and the x. What this does, though, is it changes the way that this graph looks. And now the graph looks something more comfortable, perhaps. You have y equals 2x squared, y plus x equals 1. And you'll notice that all I did here is I reflected that graph. So I took that graph and reflected it, and you get this. And it looks kind of funny because my labels are odd, but it's the same graph. If you find this area, it'll be the same as that area. So This is maybe more comfortable. Hayden? It's a reflection about the line y equals x. So if you can imagine putting your mirror here, but that's neither here nor there. This little trick, though, works in this section. There will be problems where this trick is much harder to implement later on. So you can use this trick, but it would be good for you to also become somewhat comfortable with using horizontal rectangles. All right, do your best with the homework. If you want to claim one of these unnamed papers, you can do so. It may be one of the absent people. And otherwise, we'll see you tomorrow. Thanks for all your work. You're doing great.